Welcome to day 1 of the ISO 42001 Lead-Auditor-Course. Today we will explore the fundamentals of artificial intelligence, providing you with the technical foundation needed to audit AI systems effectively. Our agenda for today covers 8 essential topics: what is AI, machine learning mechanics, supervised learning, neural networks and deep learning, large language models, classification tasks, generative AI risks, and key terms and definitions. Let us begin with topic 1. What is artificial intelligence? This foundational module will help you understand AI from an auditor's perspective. By the end of this topic, you will be able to define AI using ISO 42001-Lead-Auditor-Course terminology, understand the evolution from symbolic AI to deep learning, recognize how AI differs from traditional software, and identify AI lifecycle phases relevant to auditing. According to ISO, an AI system is an engineered system that generates outputs such as content, forecasts, recommendations, or decisions. It operates with varying levels of autonomy and uses machine-based learning and computational approaches. The key components are input, model, task, and output. Traditional software is deterministic, the same input always produces the same output. AI systems are probabilistic, they make predictions with confidence scores. AI learns patterns from data rather than being explicitly programmed, and outputs require interpretation and threshold decisions. AI has evolved significantly over the decades. The 1950s to 1970s saw symbolic AI and rule-based systems. The 1980s and 1990s brought expert systems and the AI winters. The 2000s marked the machine learning renaissance, and from 2010 to the present, we have seen the rise of deep learning and transformers. The AI lifecycle includes 4 main phases. First, design and development involving data collection and model training. Second, verification and validation for testing and bias assessment. Third, deployment for production release and integration. Fourth, operations for monitoring, maintenance, and drift detection. Remember these key points: AI systems are probabilistic, not deterministic. Auditors must understand the entire AI lifecycle. ISO 42001 applies governance across all phases of AI development and operation. Now let us move to topic 2, machine learning mechanics. This topic covers the engine behind AI systems. After this topic, you will be able to explain the data algorithm model triad, understand supervised, unsupervised, and reinforcement learning, recognize overfitting and underfitting issues, and identify key performance metrics. Machine learning has 3 core components. Data is the raw material for learning, and quality is critical. The algorithm provides the learning rules and how patterns are found. The model is the trained artifact that makes predictions. There are 3 main types of machine learning. Supervised learning uses labeled data for classification and regression. Unsupervised learning works with unlabeled data for clustering and anomaly detection. Reinforcement learning involves learning through feedback and rewards. Most enterprise AI uses supervised learning. Several quality issues can affect models. Overfitting occurs when the model memorizes training data and fails on new data. Underfitting happens when the model is too simple and misses important patterns. Bias represents systematic errors from data or algorithm choices. Variance shows sensitivity to training data fluctuations. The machine learning lifecycle flows from data ingestion to preparation to feature engineering, then to model training, validation, and testing, and finally to deployment, monitoring, and retraining. Each phase has distinct audit control points that auditors must understand. Key takeaways from this topic: data quality directly impacts model quality. Overfitting is a major risk in production systems. Continuous monitoring is essential for ML systems. Topic 3 covers supervised learning and its relevance to auditors. This is the most common type of AI you will encounter. You will learn to differentiate regression from classification problems, understand probability thresholds and their business impact, master the confusion matrix and derived metrics, and evaluate data labeling processes for quality. Supervised learning includes 2 main problem types. Regression predicts continuous values like price or temperature. Classification predicts categories like spam versus not spam or fraud versus legitimate. Binary classification has 2 possible outcomes: while multiclass has multiple possible categories. Common supervised learning algorithms include linear and logistic regression, which are simple and interpretable, decision trees, which are rule-based and easy to explain, random forests, which are ensembles of trees and robust, and support vector machines, which are good for complex boundaries. Understanding metrics is essential. Accuracy measures overall correctness but can be misleading. Precision tells us of predicted positives, how many are correct. Recall tells us of actual positives, how many did we find. F1 score is the harmonic mean of precision and recall. When auditing data labels, consider who created the labels, domain experts or crowdsourcing. Check interannotator agreement to see if labelers agree. Look for label drift where definitions may have changed over time. Identify bias in labeling from systematic errors in human judgment. Key takeaways: threshold selection is a business decision with risk implications. Never rely on accuracy alone for imbalanced datasets. Data labeling quality is foundational to model quality. Topic 4 explores neural networks and deep learning, helping you understand the black box nature of these systems. After this topic, you can explain how neural networks process information, identify common architectures like CNN, RNN, and transformer, understand the opacity challenge in XAI solutions, and recognize transfer learning risks. The basic building block is the perceptron, which takes inputs, multiplies by weights, adds bias, and applies an activation function. Networks have input, hidden, and output layers. Deep learning refers to networks with many hidden layers. Nonlinear activation functions enable learning of complex patterns. Different architectures suit different data types. CNNs or convolutional neural networks are for images and spatial data. RNNs and LSTMs are for sequential data and time series. Transformers use attention mechanisms and power language models. Each architecture is suited for specific data types. Neural networks present an audit challenge with millions of parameters and no simple explanation. Opacity makes it difficult to answer why the model made a prediction. This creates regulatory challenges around the right to explanation under GDPR Article 22. Hidden biases can be difficult to detect. Explainable AI tools help address opacity. SHIP provides Shapley additive explanations for feature importance. LIME offers local interpretable model-agnostic explanations. Attention visualization shows what the model focuses on. Surrogate models approximate complex models with interpretable ones. Remember, deep learning trades interpretability for performance. XAI tools are essential for auditing neural networks. Transfer learning can inherit biases from source models. Topic 5 covers large language models and generative AI, the technology behind systems like ChatGPT. You will learn to explain how LLMs generate text through tokenization and context, identify key risks including hallucination, data leakage, and prompt injection, understand temperature and its effects on output, and recognize security and IP risks in GenAI deployments. LLMs work through tokenization, converting text to numeric tokens. They use next token prediction, which is statistical word prediction. The context window is their limited memory, for example 128,000 tokens. Temperature controls randomness, where 0 is deterministic and 1 is creative. Key risks include hallucination, where outputs are confident but factually wrong. Data leakage, exposing sensitive information in prompts. Prompt injection, where malicious inputs manipulate behavior. Training data issues including copyright concerns, bias, and outdated information. Mitigation strategies include RAG or retrieval augmented generation for grounding outputs in facts. Content filters to block harmful inputs and outputs. Human in the loop for review before high-stakes decisions. Guardrails for output validation and sanitization. Security considerations include API key management and access controls, data residency and processing location, logging and monitoring of prompts and responses, and vendor risk assessment for third-party LLMs. Key points: LLMs are statistical predictors, not knowledge bases. Hallucination is inherent, not a bug to be fixed. Security controls must cover the entire prompt response chain. Topic 6 provides a deep dive into classification tasks and thresholds, essential for understanding AI decision-making. You will be able to distinguish binary, multi-class, and multi-label classification, understand probability thresholds and ROC curves, master the confusion matrix components, and apply appropriate metrics for imbalanced datasets. There are 3 classification types. Binary has 2 classes like yes or no, fraud or legitimate. Multi-class has multiple exclusive classes like cat, dog, or bird. Multi-label allows multiple simultaneous labels like tags on an article. Each type has different evaluation approaches. The confusion matrix has 4 components. True positive or TP means correctly predicted positive. True negative or TN means correctly predicted negative. False positive or FP is a type 1 error, also called a false alarm. False negative or FN is a type 2 error, a misdetection. Models output probabilities, and thresholds create decisions. A lower threshold means more positives, higher recall, but more false positives. A higher threshold means fewer positives, higher precision, but more false negatives. ROC and AUC evaluate performance across all thresholds. Imbalanced data is a common problem with rare events like fraud at 0.1% or disease at 1%. Solutions include resampling by oversampling the minority or undersampling the majority. Cost-sensitive learning penalizes errors differently. Stratified sampling maintains class proportions and splits. Key points: threshold selection encodes risk tolerance and business priorities. Imbalanced datasets require specialized metrics. The right threshold depends on the cost of false positives versus false negatives. Topic 7 addresses generative AI risks and ethics, helping you navigate the new risk landscape. After this topic, you can categorize GenAI risks across truthfulness, safety, legal, and societal dimensions, understand mitigation strategies like red teaming and watermarking, map risks to ISO-42001 controls, and recognize deepfake and synthetic content challenges. GenAI risks fall into 4 categories. Truthfulness risks include hallucination and misinformation. Safety risks include CBRN content, cyber weapons, and harmful advice. Legal and IP risks include copyright infringement and privacy violations. Societal risks include deepfakes, bias amplification, and manipulation. Mitigation strategies include red teaming for adversarial testing to find vulnerabilities, watermarking to embed markers in generated content, content filters for pre- and post-generation screening, human review which is mandatory for high-risk outputs. ISO 42001 provides relevant controls. Clause 6.1 covers risk assessment for GenAI applications. Clause 8.4 addresses documentation of AI system behavior. Annex B provides controls for specific AI risks. The standard integrates with existing information security management systems under ISO 27001. For deepfakes and synthetic content, detection tools use forensic analysis and metadata checks. C2PA provides content authenticity initiative standards. Provenance tracking monitors origin and modifications. Organizational policies should establish acceptable use guidelines. Key takeaways: GenAI risks span technical, legal, and ethical domains. No single control addresses all risks, so a layered approach is needed. ISO 42001 provides a framework but requires GenAI-specific controls. Our final topic is key terms and definitions, providing you with the auditor's glossary for AI governance. By the end of this topic, you will master ISO 22989 and ISO 42001 core terminology, understand the difference between governance, technical, and operational terms, recognize regulatory terminology from the EU AI Act and GDPR, and apply ethical AI vocabulary appropriately. Core governance terms include AI system and engineered system generating outputs with autonomy. AIMS, the AI management system, which is the ISO 42001 scope. AI policy, the organizational commitment to responsible AI. Interested party or stakeholder, anyone affected by the AI system. Technical terms include algorithm, a step-by-step procedure for computation. Model, a trained artifact that makes predictions.
hyperparameters, configuration settings for training,
feature, and input variable used by the model. Operational terms include model drift, the degradation of model performance over time.
continuous learning, ongoing model updates in production. HITL or human in the loop, the human oversight requirement. MLOps, DevOps practices for ML systems. Risk and ethics terms include fairness, equitable treatment across groups. Transparency, openness about AI system operation. Accountability, clear responsibility assignment. Impact assessment, formal evaluation of AI system effects. Final key points: precise terminology is essential for effective auditing. ISO standards provide authoritative definitions. Auditors must bridge technical and governance vocabulary.
This concludes Day 1 of the ISO-42001 Lead Auditor course on understanding artificial intelligence. You have learned the fundamentals of AI, machine learning, neural networks, and the key risks and terminology needed for auditing AI systems.
Thank you for your attention. Please feel free to ask any questions.